So here we're going to take a look at extensive and intensive properties. These are things that we talk about relative to a system. And the system is that part of the universe that we are interested in. It could be as small as a grain of sand, or it could be an entire planet, or even an entire galaxy. All right, so back to the properties. So what do they mean? So an extensive property is something that we can measure, but the thing that we measure is a function of the size of the system. It depends on how big the system is. Intensive properties are just the opposite. They are not a function of the size of the system. That those properties would be the same regardless of how big a part of the system that we measure. So let's draw a vertical line and just look at some comparisons. So what would be something that we would measure where the bigger the system, then the more stuff we might have? Well, it could be mass. That would be an example of an extensive property, so MASS. The bigger the system we look at, then the greater the amount of mass, the more grams or kilograms of stuff that we would have. Also, the volume. Bigger systems are going to tend to be larger in size. So volume is something that also depends on the size of the system. How about things that don't depend on the size? Well, it could be something like temperature. So let's imagine, to illustrate, let's imagine that we have a pot of water and we heat that water up to 80 degrees centigrade. It doesn't really matter, I suppose. Now, if we heat that water up, let's say we have a 5-gallon tank here, we could take a tiny little cup here, dip it into that water, and then just take a cup of that material. So instead of sampling the entire 5-gallon pot of water, we'll just take this tiny amount. But if this thing here is sitting at 80 degrees centigrade, this little amount here will also be 80 degrees centigrade. It doesn't really matter. And so we would get the same value for temperature whether we sample a small part of our system or the system as a whole. So this does not depend on the size. We would say that temperature is an intensive property, not an extensive property. What else might we have? How about the pressure? So if we have a system where it's an atmospheric pressure, so the weight of the atmosphere is bearing down on the pot, and it's also bearing down on that cup that's open to the atmosphere, then the pressure would be the same. It would be 1 atmosphere in both cases, and it doesn't matter whether we look at a small part of the system or the entire thing. But what if we look at the energy content? We had to put in a bunch of energy to get it up from, let's say, room temperature to 80 degrees centigrade. So to raise that temperature, we had to have some energy. The larger the pot we have, then the more energy we would need, right? It takes a longer time to boil 3 gallons of water than, let's say, a quart of water. And so we could put energy over on the left-hand side here. The larger system, then the more energy it's going to have. There's something else we could put over here on the right-hand side that might be a little bit less obvious, but it's concentration. So when we talk about concentration, let's say we're going to take some salt crystals and sprinkle them through this pot of water, where I think we started out with 5 gallons. If we dip our cup in after we've added the salt and stirred the system very well, then if this pot originally had, let's say, 10 ppm of salt, then that little cup would have 10 ppm also. The concentration of salt that we would measure would not depend on whether we're sampling a small part of the system or the entire thing. But of course, the mass for that amount of water and this amount of water here would be very different. The volumes would be different, and the energy content in this little cup here and this entire container here would be different. So mass, volume, energy, those are all extensive properties. Temperature, pressure, and things like chemical concentrations, those would be intensive properties. Let's take a final look at the issue. By looking at tables in Robie et al., let's say we want to compare calcite, and we want to look at its Gibbs Free Energy formation from the elements with dolomite. Dolomite has a formula that's usually written like this, and this is the way it's written in Robie et al. Too. Now, the Gibbs Free Energy formation for calcite is listed in Robie et al. As minus 1128 about 842, and that's in units of kilojoules per mole. And here we have for dolomite minus 2161 0.672 kilojoules per mole. So what we've done is we've taken energy here and we've divided it by the size of the system, where the size is defined as 1 mole. So in this case, it's not just energy, but it's molar energy. So these aren't just energies. These are molar energies. Usually we put a line over the top of these. So we have the Gibbs free energy would be the total energy of the system, but the molar Gibbs free energy, that would be an intensive property. So this is something that depends not on the size of the system, or actually we're cheating a little bit. We're saying the size of the system is 1 mole. It's the energy per mole. We could do the same thing with the volume. We could look at the volume per mole of substance, and that would also be an intensive property because we're defining the size of the system. But if we want to compare these two things, notice that the sizes of these two systems are very different. This fellow here has 5 atoms, and this fellow over here has 10 atoms. So we have twice as many atoms making up the dolomite system versus the calcite system if we just have 1 mole of each, and we define 1 mole by those formulas. So if we wanted to make a more careful comparison of who has the greater or lesser Gibbs free energy formation of the elements, we can't look at these precisely the way they're listed. Even though these are both as intensive properties because we've defined the system, we're looking at systems that have totally different numbers of atoms. And so what we would have to do is, well, one of two things. Since this is twice as large as this fellow, we can simply double that, or we can cut this in half. Let's cut this one in half. So if we did that, we would have a half an atom of calcium. We're just going to take this fellow and cut it in half. We'll have a half an atom of magnesium, and then instead of 2 carbonates, we'll just have 1. And if we cut the amount of atoms in half, we have to cut this in half also. And so dolomite on a 3-oxygen basis, that's the way we talk about it. This fellow here has 6 oxygens, so we would say it's a carbonate on the basis of 6 oxygens. Both of these are now a carbonate on the basis of 3 oxygens. Well, dolomite on the basis of 3 oxygens would have a Gibbs free energy of formation from the elements of 1080 point about 836 or so. That's basically just 1/2 of this. So now you can compare these a little more directly. They're not perfectly comparable because one has a magnesium atom here and magnesium doesn't exist over here. So if we're looking at the Gibbs free energy of the formation of the elements, we're still comparing apples to oranges. Well, maybe instead of apples, it's a Fuji compared to a Red Delicious. We're getting a little bit closer in the comparison because we're at least looking at things that are about the same size. So there are these games that we have to play. We can play some tricks where we take something like volume, which is measured in cubic centimeters, so that would be V, and we convert it into a molar volume, which we measure in, let's say, cubic centimeters per mole. This one is an extensive property, this one is an intensive property. And we could do the same with energy, as we've just shown here. But when we're comparing formulas of stuff, we really need to be careful about counting atoms. And it always depends on the kinds of things we want to compare. So that's it for extensive and intensive properties. In another video, we'll look at some of the computational effects of this.